There is a place in our solar system that almost nobody talks about. A world, or rather a collection of worlds, that has never been visited by a single spacecraft, never been photographed up close, never been sampled, probed, or studied from anything other than a distance so vast that the images we have of them look like blurry smudges on a television screen that hasn't been tuned in properly. And the reason we haven't gone there isn't budget. It isn't technology. It isn't even politics, though those things have all played a role. The real reason is buried inside a document that very few people have ever read, a risk assessment so quietly damning that it effectively killed multiple missions before they ever left the drawing board. And when you understand what's actually in that document, and what's actually waiting for us around Uranus, the whole story becomes one of the strangest and most fascinating in the entire history of space exploration. If you're the kind of person who finds that interesting, stick around because we're going to go deep on this one. And if you want more videos like this, subscribe now, because we cover the kind of space science that doesn't make the headline news but absolutely should. So let's start at the beginning. Most people learn about Uranus in school and move on within about 30 seconds, because there genuinely isn't that much in a standard science textbook to hold your attention. It's the seventh planet from the Sun. It's blue-green. It's cold. It has rings. It has moons. Next planet, please. And that's basically where most people's understanding of Uranus ends. But here's the thing. Uranus is one of the most scientifically bizarre objects in the entire solar system. And its moons, the ones nobody has ever visited, might be among the most important targets for exploration that we have. Not just in terms of scientific curiosity, but in terms of potentially finding conditions that could support life. That last sentence is one that tends to make people sit up a little straighter. So let's unpack all of it, starting with what Uranus actually is. Because like Jupiter, almost everything you think you know about it is at best incomplete and at worst completely wrong. Uranus is classified as an ice giant. That name is already a little misleading because when most people hear the word ice, they picture frozen water, the kind of thing you chip off your windshield in winter. But the ice in ice giant refers to something quite different. In planetary science, the term ice is used to describe a category of compounds, things like water, ammonia, and methane, that under normal conditions on Earth would be gases or liquids, but that form into exotic, high-pressure states deep inside a planet like Uranus. So when scientists say Uranus is an ice giant, they mean it's mostly made of these compounds in a hot, dense, pressurized form that doesn't really resemble ice in any way you'd recognize. Think of it less as a frozen ball and more as a boiling, churning, high-pressure soup of exotic chemistry wrapped in a thin atmosphere of hydrogen and helium. That's a very different mental image from what the textbooks give you. Now here's where it starts to get genuinely strange. Uranus is tilted. Not slightly tilted, the way Earth is tilted at 23 degrees and gives us our seasons. Uranus is tilted at 98 degrees. For all practical purposes, it is rolling around the Sun on its side. Its north pole points almost directly at the Sun for half of its orbit, and its south pole points almost directly at the Sun for the other half. Each pole gets roughly 42 years of continuous sunlight, followed by 42 years of complete darkness. Imagine a place that doesn't have seasons. It has something far more extreme. It has half a lifetime of day, followed by half a lifetime of night, with no transition in between. Scientists don't fully understand why Uranus is tilted like this. The most widely accepted theory is that something massive hit it early in the solar system's history. A collision so powerful that it knocked the planet sideways and it never quite recovered. But that's just a theory, and there are enough unexplained things about Uranus that some researchers have suggested the tilt might have been caused by something more gradual, like the gravitational influence of a large moon that no longer exists, or some interaction with the early protoplanetary disk. Nobody knows for certain. What makes the tilt even stranger is what it does to Uranus's atmosphere and its weather. By every model we have, a planet receiving that kind of extreme, lopsided heating from the Sun should have enormous, violent weather systems. The pole baking in sunlight for decades should generate massive storms. The temperature difference between the sunlit and dark hemispheres should drive powerful winds. And yet Uranus is, atmospherically speaking, almost eerily calm. Neptune, the next planet out, receives less sunlight, but has some of the most violent winds in the solar system. Uranus, which receives more energy and has more extreme heating patterns, is comparatively quiet. This is sometimes called the Uranus energy problem, and it has never been satisfactorily resolved. Uranus seems to be holding on to far less internal heat than it should. Neptune radiates about 2.5 times more heat than it receives from the Sun. Uranus radiates almost none beyond what the Sun gives it. Something inside Uranus is either absorbing heat unusually effectively, or there's some mechanism preventing heat from escaping. Nobody knows what it is. So before we even get to the moons, we already have a planet that is sitting on a stack of unresolved scientific mysteries, a world that doesn't behave the way our models say it should. And this is actually part of why the moons matter so much, because the moons of Uranus are geologically connected to the planet in ways that we're only beginning to understand, and studying them could help unlock answers to questions that go far beyond just what's happening at the seventh planet from the Sun. Uranus has 27 known moons. They are all named after characters from the works of William Shakespeare and Alexander Pope, which is unusual and kind of wonderful, and something almost nobody seems to know. The largest 5 are Miranda, Ariel, Umbriel, Titania, and Oberon. These 5 are the ones that matter most for our story, and they are genuinely fascinating objects in their own right. Let's start with Miranda, because Miranda is the one that tends to stop planetary scientists in their tracks the first time they really look at it. Miranda is a small moon. It's only about 470 kilometers across, which makes it tiny by solar system standards, but its surface is one of the most geologically extreme environments we know of anywhere in the solar system. The one set of close-up images we have of Miranda, and we only have images of one hemisphere, which we'll come back to, shows a world that looks like it was assembled by someone who couldn't make up their mind about what kind of planet they wanted to create. There are ancient, heavily cratered plains right next to enormous, chaotic regions of canyons and cliffs and ridges. There is a feature on Miranda called Verona Rupes, which is a cliff face estimated to be between 5 and 10 kilometers tall. That would make it the tallest known cliff in the solar system. On Miranda's low gravity, if you were standing at the top of Verona Rupes and you fell off the edge, you would fall for roughly 12 minutes before hitting the bottom. 12 minutes. You'd have time to have a fairly long conversation on the way down. Obviously, at the end of that conversation, things would not go well for you, but the point is that this is an extraordinary geological feature on what appears from a distance to be a completely unremarkable little moon. The surface of Miranda looks the way it does because something dramatic happened to it. One leading theory is that Miranda was actually shattered by a massive impact early in the solar system's history, and then the pieces slowly reassembled under gravity but in a chaotic, jumbled way, like dropping a ball of clay on the floor and pushing all the pieces back together without worrying too much about getting them back in the right order. Another theory is that Miranda experienced something called tidal heating, where the gravitational influence of Uranus periodically squeezed the interior of the moon enough to drive geological activity, volcanoes, tectonic movement, cryovolcanism, that reshaped its surface over time. The problem is that we only have images of one hemisphere of Miranda. The other half of this world is completely unknown. We have never seen it. We have no idea what's there. It could be completely different from everything we've observed. It could hold answers to questions we can't even properly formulate yet because we don't know what we're missing. Ariel is the next moon worth dwelling on, and in many ways it's the most geologically active-looking of the large Uranian moons. Its surface is covered in valleys and canyons that appear to have been carved by geological processes, and critically, it shows signs of relatively recent resurfacing, meaning that some force has been reshaping its surface comparatively recently in geological terms. This is scientifically significant because it suggests that Ariel might have, or might have had, a liquid interior. Some researchers have proposed that Ariel could harbor, or could once have harbored, a subsurface ocean. That's not a fringe idea. It's a hypothesis that's been seriously considered in peer-reviewed literature. Umbriel is almost the opposite of Ariel in terms of character. Where Ariel is bright and heavily modified, Umbriel is dark and ancient. Its surface is one of the darkest in the solar system and is covered in old impact craters, suggesting that very little has happened to it geologically for billions of years. But there's one feature on Umbriel that has puzzled scientists since Voyager 2 first spotted it. a bright ring on the floor of one crater that stands out dramatically against the dark surrounding terrain. Nobody has a fully satisfying explanation for what that ring is, or how it formed. It's just sitting there being mysterious, and we don't have the resolution or the data to say anything definitive about it. Titania is the largest of Uranus's moons, and like Ariel, it shows evidence of past geological activity. There are enormous canyons on Titania that suggest the moon's interior expanded at some point, cracking the surface from within. This kind of feature is associated with the freezing of a subsurface ocean. When water freezes, it expands, and if a moon has a liquid interior that gradually freezes, it literally cracks its own crust from the inside. This is one of the lines of evidence that has led researchers to seriously consider whether Titania, and possibly Ariel, might have liquid layers beneath their surfaces today, not just in the ancient past, but right now. And then there's Oberon, the outermost of the large moons, heavily cratered and ancient-looking, with some interesting mountain features that haven't been well explained. Like all of these moons, we have only the most basic data about it, enough to raise questions, not nearly enough to answer them. Here is the critical thing to understand about everything we know about these 5 moons. Almost all of it comes from a single source: one spacecraft, one flyby, one shot. In January 1986, NASA's Voyager 2 spacecraft swept past Uranus on its grand tour of the outer solar system. It was moving fast. It had roughly 6 hours of close observation time at the Uranian system, 6 hours to study a planet, its rings, and all of its moons, after which it was gone forever, continuing on toward Neptune. In those 6 hours, Voyager 2 changed everything we know about Uranus and its moons. But it also left us with an agonizing amount of incomplete information, because 6 hours is almost nothing when you're trying to understand a planetary system. Voyager 2 could only photograph the sunlit hemisphere of Miranda, which is why we've never seen the other side. It got reasonable coverage of Ariel and Titania, decent coverage of Umbriel, and relatively good coverage of Oberon, but the geometry of the flyby, the speed of the spacecraft, and the lighting conditions all imposed severe constraints on what could be observed. Some moons were in shadow for much of the encounter, resolution was limited, and many of the smaller inner moons were only barely detected. Several moons that we now know exist weren't discovered until years later using Hubble and ground-based telescopes. So when we talk about what we know about Uranus's moons, we are talking about what we learned in a single 6-hour window nearly 4 decades ago. Everything else is inference, modeling, and educated guesswork. Which brings us to the central question of this story. Why haven't we gone back? This is where the story gets complicated, and this is where that risk assessment starts to become relevant. If you look at NASA's mission history for the outer solar system, the pattern is striking. Jupiter has been visited by Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Ulysses, Cassini during a gravity assist, New Horizons during a gravity assist, and most prominently by the Galileo spacecraft which orbited Jupiter for 8 years and deployed a probe into its atmosphere, and currently by the Juno spacecraft which is still operating. Saturn was orbited by Cassini for 13 years. 13 years. Cassini gave us data that scientists are still actively publishing research papers from today. We sent Huygens to land on Titan. We studied Saturn's rings in extraordinary detail. We discovered that Enceladus has a subsurface ocean that is actively venting material into space. Saturn has been extraordinarily well studied. Neptune got a Voyager 2 flyby in 1989, and that's it. No dedicated mission has ever gone back. And Uranus? Same story. One flyby in 1986, and then nothing. For nearly 40 years, nothing. No orbiters, no probes, no dedicated flybys. Uranus and its moons have been essentially ignored by interplanetary exploration. Now, there are real and legitimate reasons that missions to Uranus are difficult. The planet is far. On average, it's about 19 astronomical units from the Sun, about 19 times the distance from the Earth to the Sun. At that distance, a signal traveling at the speed of light takes roughly 2.5 hours to reach us from Uranus. Power is a constant challenge, because solar panels become essentially useless that far from the Sun, so missions have to run on nuclear power in the form of radioisotope thermoelectric generators. and the geometry of the solar system creates what are called launch windows, specific periods where the alignment of planets makes a trajectory feasible. And for Uranus, those windows don't come around frequently. Miss a window, and you might be waiting a decade for the next reasonable opportunity. All of this is true, all of this is real, all of this contributes to why we haven't been back. But it doesn't fully explain it. Because if scientific priority were the deciding factor, Uranus and its moons would arguably rank near the top of the list. The potential for subsurface oceans on Titania and Ariel alone should have been enough to make the system a high-priority target after the discoveries at Europa and Enceladus transformed our understanding of where life might exist in the solar system. And yet, decade after decade, mission proposals for Uranus have been written, studied, shortlisted, and then set aside. The real story lives in a combination of technical risk, operational complexity, and a series of planning documents that don't get much public attention, but that collectively paint a picture of a destination that is genuinely, uniquely difficult in ways that go beyond simple distance. Let's talk about the nature of that difficulty, because it's not obvious. The first challenge is what's called the radiation environment. Uranus has a magnetic field, and like all magnetic fields in the outer solar system, it traps charged particles and creates radiation belts around the planet. These radiation belts are similar in concept to Earth's Van Allen belts, but in the context of a spacecraft, they represent a serious engineering problem. Electronics don't like radiation. Radiation causes bit flips, damages solar cells, degrades sensors, and over time can cause catastrophic failures in spacecraft systems. The radiation environment around Jupiter is so severe that it was a major design constraint for the Juno spacecraft, and was one of the primary reasons Galileo eventually stopped functioning. The radiation environment around Uranus is less intense than Jupiter's, but it's still significant, and it interacts with the moons in ways that are poorly understood because we simply don't have enough data. Here's the specific problem with Uranus's radiation environment that most people don't appreciate. The magnetic field of Uranus is not centered on the planet. On Earth and on most planets with magnetic fields, the magnetic axis runs roughly through the center of the planet and is roughly aligned with the rotation axis. Uranus is different. Its magnetic field is offset from the center of the planet by a significant amount, and it's tilted relative to the rotation axis by about 60 degrees. Combined with the planet's extreme axial tilt, this produces a magnetic field that wobbles and gyrates in a complex, almost chaotic way as the planet rotates. The result is that the radiation environment around Uranus doesn't have a stable, predictable structure the way it does around Jupiter. It changes dramatically depending on where you are in your orbit around the planet, and those changes happen on timescales of hours. This makes it very difficult to plan a spacecraft's trajectory in advance to minimize radiation exposure, because the radiation environment your spacecraft will encounter depends on the exact timing of where you are relative to a field that is constantly shifting. Mission planners have to essentially accept a high degree of uncertainty about the total radiation dose a spacecraft will accumulate over a multi-year mission, and that uncertainty feeds directly into risk assessments in ways that are difficult to manage. The second challenge is the thermal environment, and this is one that is genuinely underappreciated in public discussions of outer solar system exploration. At Uranus's distance from the Sun, temperatures in space drop to around -215 degrees Celsius. Spacecraft electronics, fuel lines, mechanisms, all of these have operating temperature ranges, and keeping them within those ranges requires careful thermal management. At the same time, many of the scientific instruments on a spacecraft generate heat themselves, and managing that heat, keeping some systems warm enough to function while preventing others from overheating in the vacuum of space, is an engineering challenge that gets more complex the farther from the Sun you go. The Voyager spacecraft dealt with this, and it's manageable. But for a spacecraft designed to spend years in orbit around Uranus, rather than just passing through on a flyby, the thermal management requirements become much more stringent. The third challenge, and arguably the most significant for the specific question of visiting the moons, is the orbital mechanics of the Uranian system itself. Here's the issue. Uranus's extreme axial tilt means that its moons orbit in a plane that is nearly perpendicular to the planet's orbital plane around the Sun. If you imagine the solar system as a flat disk, Uranus's moons are orbiting in a nearly vertical circle relative to that disk. This has profound consequences for how a spacecraft can approach the system. Almost every trajectory that gets a spacecraft from Earth to Uranus arrives in the plane of the solar system, which means arriving roughly perpendicular to the plane of the moon's orbits. To get into an orbit that allows you to visit the moons, you have to change your orbital plane significantly. And changing orbital planes in space is enormously expensive in terms of propellant. It's one of the most fuel-intensive maneuvers in spaceflight. Carrying enough propellant to achieve that plane change, while also carrying all the fuel needed to slow down and insert into orbit around Uranus in the first place, massively increases the size and mass and cost of the spacecraft. Mission planners have struggled repeatedly with this problem, trying to find trajectories that minimize the plane change requirement while still getting a spacecraft into a useful science orbit, and the solutions are always compromises that sacrifice something important. The fourth challenge is the communication problem. We mentioned signal travel time, about 2.5 hours at the current average distance. But the deeper problem is data rate. At Uranus's distance, the radio signals from a spacecraft are extraordinarily faint by the time they reach Earth. Even with the powerful deep space network antennas that NASA uses to communicate with distant spacecraft, the amount of data you can receive per day from a spacecraft at Uranus is limited. This means that even if a spacecraft is gathering enormous amounts of data, it may take weeks or months to send that data home. For a mission to the moons, where you want high-resolution images, spectroscopy data, magnetometer readings, and measurements from multiple instruments, the data rate limitation is a constant constraint on what science can actually be accomplished within a mission's lifetime. Now, all of these challenges are real, but they're not unprecedented. NASA has dealt with similar challenges at Jupiter and Saturn. The Cassini mission to Saturn operated in a challenging radiation environment, managed extreme thermal conditions, and dealt with data rate limitations throughout its 13-year mission. These problems can be engineered around. They make missions harder and more expensive, but they don't make them impossible. So why haven't we gone back to Uranus? The answer, as best as can be pieced together from mission planning documents, planetary science decadal surveys, and the history of NASA mission development, comes down to something more fundamental than any individual technical challenge. It comes down to how risk is assessed and prioritized in an environment of limited resources. And this is where that unpublished risk assessment, or more precisely, the series of assessments and planning documents that constitute the effective risk picture, becomes so revealing. In the United States, NASA's priorities for planetary science are set roughly every decade by a process called the Planetary Science Decadal Survey. This is carried out by the National Academies of Sciences, Engineering, and Medicine, and it involves the broader planetary science community identifying the most important scientific questions and recommending specific missions to address them. The decadal survey process is enormously influential. If a mission gets recommended by the decadal survey, it has a much better chance of actually getting funded and built. If it doesn't make the list, it tends to languish. Uranus has been on the radar of the decadal survey community for a long time, but for many years it kept getting pushed down the priority list in favor of targets that were considered more scientifically urgent: Mars, the outer moon systems of Jupiter and Saturn, the search for biosignatures at places like Europa and Enceladus. The argument was always that other destinations offered a clearer and more immediate path to answering the most important questions, particularly questions about life. Uranus, despite its mysteries, was seen as more of a secondary priority. That changed significantly with the 2023-2032 Planetary Science Decadal Survey, known informally as the Origins, Worlds, and Life Survey. For the first time, a Uranus orbiter and probe mission was ranked as the top priority for a large, flagship-class mission. This was a major shift. The scientific community essentially declared that studying Uranus, its interior, its atmosphere, its rings, and critically its moons, was the single most important large mission objective for planetary science in the coming decade. This led to serious planning discussions and studies, and brought the question of how to actually do a Uranus mission back to the forefront of NASA's thinking. But here's where the risk picture becomes really interesting, because the detailed mission studies that followed that recommendation revealed just how constrained the options really are, and why the history of not going to Uranus isn't simply a story of neglect. One of the mission concepts that has been studied in detail is called the Uranus Orbiter and Probe. It involves a flagship-class spacecraft that would orbit Uranus and deploy an atmospheric probe, similar in concept to what Galileo did at Jupiter. The science case for this mission is compelling. An orbiter could study the planet's interior using gravity measurements, map its magnetic field in detail, study its rings, and most importantly, make multiple close passes of the major moons. The atmospheric probe would give us our first direct look at the composition of Uranus's interior, which would help resolve fundamental questions about how ice giants form and whether Uranus and Neptune are actually representative of the most common type of planet in the galaxy. Because current exoplanet surveys suggest that planets in the size range of Uranus and Neptune may be the most abundant type of planet around other stars. But the detailed risk assessments for this mission, which have been carried out by NASA's Jet Propulsion Laboratory and other mission study teams, reveal a set of concerns that are sobering. The first set of concerns relates to the radiation environment we discussed. Because Uranus's magnetic field is so chaotic and offset, mission planners have struggled to define a safe orbital trajectory that avoids the highest radiation regions while still allowing the spacecraft to visit the moons and conduct useful science. The moons themselves are embedded in Uranus's magnetosphere, which means any close flyby of a moon involves flying through a region of elevated radiation. The concern isn't that a single flyby would destroy the spacecraft. The concern is the cumulative radiation dose over a multi-year mission involving dozens of moon flybys. At some point, the radiation damage to the spacecraft's electronics becomes a serious operational risk. Exactly when that threshold is reached depends on factors, like the detailed structure of Uranus's radiation belts, that we simply don't know well enough to model accurately, because our data on Uranus's magnetosphere comes almost entirely from that 6-hour Voyager 2 flyby nearly 40 years ago. This creates a situation where mission planners cannot give a confident answer to the question of how long the spacecraft will function. And if you're asking for $1 billion or more in mission funding, we're not sure exactly how much of the science we'll actually get to do, is a deeply uncomfortable answer to have. The second set of concerns is about power. We've mentioned that solar panels don't work well at Uranus's distance from the Sun. This means the spacecraft needs to run on radioisotope thermoelectric generators. These are devices that convert the heat from the natural radioactive decay of plutonium-238 into electricity. They're reliable, long-lived, and they're the power source used by Voyager, Cassini, New Horizons, and many other deep space missions. But there's a problem. The supply of plutonium-238 available to NASA is limited. Producing it requires operating specific nuclear reactors, and production has historically been intermittent and insufficient to meet all of NASA's needs. There have been periods where the plutonium supply was so constrained that it was a genuine limiting factor in how many nuclear-powered missions could be flown. A flagship mission to Uranus would require a significant plutonium allocation, which means it would be competing with other missions that also need that resource. The third concern, and this is the one that doesn't get discussed publicly in clear, plain terms very often, is what might be called the single point of failure problem. A flagship mission to Uranus represents an enormous investment. We're talking about a spacecraft that would take somewhere between 10 and 13 years just to travel from Earth to Uranus. So if you launch in the mid-2030s, which is the earliest realistic window given current planning timelines, you're looking at arriving in the late 2040s or early 2050s. Whatever science you're hoping to do with that mission will not begin until the 2040s. And all of that, the $1 billion+, the years of engineering, the careers of hundreds of scientists and engineers, rides on a single spacecraft that has to operate correctly after a decade of interplanetary travel, survive the radiation environment, function in the extreme cold, and execute complex maneuvers with no possibility of repair or rescue if something goes wrong. If anything fails catastrophically, the entire scientific return is lost. There is no fallback. There is no repair mission. Now, this isn't unique to Uranus. It's true of essentially every flagship mission in deep space. But the specific combination of factors at Uranus, the long travel time, the uncertain radiation environment, the thermal challenges, the orbital mechanics complexity, makes the risk profile harder to characterize clearly than at, say, Saturn. And that difficulty in characterization is itself a risk. Engineers and mission planners can work with known risks. They can design around them, mitigate them, accept them with clear eyes. What they can't easily work with is risks they can't quantify, because an unquantified risk can become catastrophic without warning. This is what sits at the heart of the story. Not a single dramatic document that killed a Uranus mission, not a conspiracy or a cover-up, but rather an accumulation of technical uncertainties, each individually manageable, that together create a risk profile for a Uranus moon mission that is genuinely more difficult to characterize and defend than comparable missions to other destinations. And in a competitive environment where missions are funded based on their expected scientific return relative to their cost and risk, those uncharacterized risks are a significant disadvantage. Let's talk specifically about what a mission to the moons would look like, because this is really the heart of what we're missing. A dedicated Uranian moon mission, one optimized not just to orbit the planet, but to extensively study the 5 major moons, would be one of the most complex and ambitious missions ever attempted in solar system exploration. The reason is the orbital geometry problem we described earlier, combined with the sheer number of targets. Each of the 5 major moons is a scientifically interesting world in its own right. Miranda's bizarre geology needs to be properly mapped, all of it, including the hemisphere we've never seen. Ariel's geological activity needs to be characterized. The question of whether Titania and Ariel have subsurface oceans needs to be answered definitively. Umbriel's dark surface and mysterious bright ring need to be studied up close. Oberon's mountains need to be mapped. Each of these goals requires multiple close flybys at low altitude, which means the spacecraft needs to change its orbit repeatedly to target different moons, which costs propellant, which adds mass. The subsurface ocean question is particularly important because it has direct implications for the search for life beyond Earth. The discovery that Europa, one of Jupiter's moons, likely has a global liquid water ocean beneath its icy crust was transformative for astrobiology. It showed that liquid water, the most basic requirement for life as we know it, could exist in the outer solar system, far from the warmth of the sun, maintained by the heat generated by tidal forces. Since then, we've found strong evidence for subsurface oceans at Enceladus, Titan, Ganymede, and Callisto. The outer solar system appears to be full of liquid water. The question has gone from whether life could exist out there to where specifically it might be most likely to take hold. In this context, Titania and Ariel are not just interesting geology, they are potential abodes for life, and we have essentially no data on them beyond those 6 hours from 1986. Researchers who have modeled the interiors of these moons, using our knowledge of their masses, their densities, their surface characteristics, and theoretical models of how moons evolve over time, have concluded that liquid water could plausibly exist beneath the surfaces of both Ariel and Titania today. The mechanism would be a combination of radiogenic heating from the decay of radioactive elements in the moon's rocky interiors and possibly some residual tidal heating from the gravitational interaction with Uranus. The amount of heat available isn't as large as what Europa gets from its interaction with Jupiter's powerful gravity, but it may be enough to maintain pockets or layers of liquid water at depth, especially if there are dissolved salts in the water that lower its freezing point, as appears to be the case at Enceladus. There is also recent research that has complicated the picture in an interesting way. Analysis of data from Voyager 2, combined with new modeling work, has suggested that Ariel, and possibly other moons, may be releasing material into space, in a form similar to Enceladus's famous geysers, but much more subtle and harder to detect. If that's true, it would mean that a spacecraft passing through the Uranian system isn't just visiting inert, icy worlds, it's potentially flying through material that has been ejected from the interiors of those worlds, material that, if analyzed correctly, could directly reveal the chemical composition of a subsurface ocean. This is exactly what the Cassini mission did at Enceladus, and the results were revolutionary. Evidence for complex organic chemistry, evidence for the right conditions for life, all from flying through a plume. The prospect of doing the same thing at Ariel, or another Uranian moon, is one of the most compelling arguments for going there, and it's one of the reasons that the 2023 Decadal Survey ranked a Uranus mission so highly. But here's the thing. That analysis of Ariel's potential activity, that recent modeling work, comes from researchers working with 40-year-old data combined with computer simulations. It's compelling. It's taken seriously by the scientific community, but it cannot be confirmed or refuted without going there. And going there, as we've established, involves a complex and expensive mission with a risk profile that's hard to fully characterize in advance. Let's talk about another layer of this story that often gets overlooked, which is what we don't even know we don't know. In science, there's a useful distinction between known unknowns and unknown unknowns. Known unknowns are things we've identified as gaps in our knowledge. We know we don't know the answer, and we have a rough idea of what answering the question might reveal. Unknown unknowns are things we don't even know we're missing, gaps in our understanding that we're not aware exist because we haven't gathered the basic data necessary to identify them. The Voyager 2 flyby of Uranus was extraordinary for its time, but it was a single flyby in a single geometry at a single moment in time, with instruments designed in the 1970s. The amount of unknown unknowns that it left behind is enormous. We don't know what the other side of Miranda looks like. We don't know what Uranus's magnetosphere looks like at a different phase of the planet's rotation. We don't know what seasonal changes look like in the Uranian system. And remember, a season on Uranus lasts 42 years, so Voyager 2 saw a single snapshot of a system that was in a very specific seasonal configuration at the time. We don't know the detailed compositions of the moon's surfaces. We don't know the internal structures of the moons. We don't even have a full census of the smaller moons. There are likely moons in the Uranian system that we haven't discovered yet. Every mission to a previously visited part of the solar system has discovered things that weren't expected. Cassini discovered Enceladus's plumes when nothing in the Voyager data had suggested they were there. Juno discovered that Jupiter's interior is far more complicated than models had predicted. New Horizons revealed that Pluto, tiny, distant, seemingly dead Pluto, has nitrogen glaciers and a possible subsurface ocean and mountains made of water ice. In every case, the surprises were things that simply could not have been predicted from the data we had before those missions arrived. The Uranian system, with its 40-year gap in observations and its stack of unresolved mysteries, is probably harboring surprises that would rewrite textbooks. We just don't know which textbooks yet. And this is actually the most frustrating dimension of the whole story. The scientific case for going to Uranus and its moons is not just strong, it is arguably one of the strongest cases in planetary science. Ice giants may be the most common type of planet in the galaxy. We have almost no understanding of how they form, how they work internally, or what their moon systems are really like. The moons of Uranus may have liquid water oceans that could, in principle, harbor life. The magnetic field of Uranus is one of the strangest in the solar system and is poorly understood. The atmosphere of Uranus holds the answer to a fundamental mystery about planetary energy balance that our current models can't explain. The geology of Miranda alone would justify a dedicated mission. The case for going is overwhelming. The barriers to going are real but not insurmountable. And yet, here we are in the mid-2020s, with the earliest realistic arrival date for a Uranus orbiter being sometime in the late 2040s or early 2050s, meaning that by the time a spacecraft first enters orbit around Uranus, it will have been roughly 65 to 70 years since Voyager 2's flyby. 65 years of waiting. 65 years of looking at blurry images and running computer simulations and arguing about whether those smudges in the Hubble data might be evidence of something extraordinary. Let's be specific about what the current mission planning situation looks like, because this is an area where there's been genuine progress, despite all the difficulties. Following the 2023 Decadal Survey's top recommendation, NASA has been conducting formal mission studies for the Uranus orbiter and probe concept. These studies are serious engineering exercises, not just scientific wish lists. They involve actual trajectory analysis, spacecraft design concepts, instrument suite selection, power system planning, and crucially, risk assessment. The studies have identified the mid-2030s as the optimal launch window, specifically around 2031 to 2038, with the exact timing determined by the need for a gravity assist from Jupiter, which significantly reduces the travel time and fuel requirements. Miss that window, and the next reasonable opportunity doesn't come for many years. The spacecraft concepts that have been developed are sophisticated. They involve a main orbiter spacecraft that would carry a suite of scientific instruments, and an atmospheric probe that would be released to descend into Uranus's atmosphere and transmit data back before being crushed by the pressure. The orbiter would use multiple gravity assists during its approach to the Uranian system to shape its orbit for moon science, but the orbital geometry challenges remain and represent a real constraint on how many high-quality moon flybys can be achieved. The instruments being considered for the orbiter would be transformative if they work as planned. A magnetometer to map Uranus's chaotic magnetic field in detail, an ice-penetrating radar that could potentially detect subsurface liquid water layers in the moons, similar to instruments that have been used to map the subsurface of Mars, mass spectrometers to analyze any material that the moons might be venting into space, cameras operating in multiple wavelengths to map moon surfaces in unprecedented detail, gravity science instruments to probe the internal structures of the moons through subtle measurements of how their gravity affects the spacecraft's trajectory. If this mission launches on schedule, operates as designed, and makes it to Uranus, all of which are big ifs in the complicated world of spaceflight, the scientific return could be epoch-defining, the kind of mission that produces discoveries that scientists talk about for generations. But there's still that risk picture, and it's still not fully characterized, because to fully characterize the radiation environment, the magnetic field structure, the moon activity, and all the other factors that feed into a complete risk assessment, you need data from the Uranian system. Data that you can only get by going to the Uranian system. There's a circular quality to this problem that makes it genuinely difficult to resolve from Earth. The best pre-arrival models will still leave significant uncertainties that can only be resolved once the spacecraft is actually there. Mission planners have to design around a range of possible environments rather than a precisely known one, and that design to a range approach adds mass, adds cost, and still leaves residual uncertainty. This is not a reason not to go. It's a reason why the decision to go requires a certain kind of institutional courage, the willingness to commit to a decades-long investment with imperfect knowledge,